Hello and welcome to the Abingdon Physics YouTube channel. Today we'll be looking at IGCSE Edexcel Physics, Topic 6, Magnetism and Electromagnetism, in particular Electromagnetic Induction. So we will first be covering spec points 6.15 and 6.16 for double award, and then we will be looking at 6.17 to 6.20, which will be for triple award only. So double award for the first part of the video, then triple award for the whole video. So our first spec point is 6.15. Know that a voltage is induced in a conductor or a coil when it moves through a magnetic field or when a magnetic field changes through it, and describe the factors that affect the size of the induced voltage. So the way that this is normally expressed in GCSE physics is that we have a wire moving through a magnetic field. Now, when a wire moves through a magnetic field, it cuts through the field lines. Often in mark schemes, that word cuts is bolded, and so the GCSE mark scheme really wants you to use that word cuts. And when it cuts through the field lines, it induces a voltage in the wire. And that word induces must be used alongside the word voltage. So we're having cut field lines, inducing a voltage in the wire. And if we were to move the wire faster, we would be cutting more field lines per second. Therefore, we would be inducing a larger voltage. If the magnetic field was stronger, because the field lines were closer together, then if we moved the wire through the field, we would cut more field lines per second, and the induced voltage would be larger again. So we can apply this principle in action for spec point 6.16, which says to describe the generation of electricity by the rotation of a magnet within a coil of wire, and of a coil of wire within a magnetic field, and describe the factors that affect the size of the induced voltage. So this is the generator effect. On screen now there is an image of a generator, and as the handle is turned, the coil moves through the magnetic field. Now, we stated before, when a coil moves through a magnetic field, it cuts the field lines between the permanent magnet. And when it cuts those field lines, there is an induced voltage in the coil, and therefore it can be connected to a battery. So this is how a generator works. We're turning the handle, therefore the coil is cutting the magnetic field lines, therefore a voltage is induced, and therefore there will be a current through the circuit because it is a complete circuit. There will only be a current through the circuit if it is a complete circuit. That is a really important point. But for double award, the words we are really making sure we are using are field lines being cut and voltage being induced. If we somehow managed to make a system where the magnet moved and the coil stayed in the same place, it would be the exact same procedure, as the field lines would still be being cut by the coil, and therefore a voltage would still be being induced. It would be the same principle if the magnet was moving instead of the coil. So how could we increase the size of the induced voltage? Well, there are two simple ways. The first way is to increase the strength of the magnetic field, therefore more field lines would be being cut per second. Or we could spin the coil faster, therefore also cutting more field lines per second, and therefore inducing a larger voltage. So how might we see this as a question in GCSE physics? Well, we have the same diagram, and it's asking us to explain how the generator produces a voltage. Well, turning the handle causes the coil to rotate, therefore the coil is cutting the magnetic field lines and inducing a voltage. And if we check our mark scheme, this is exactly what we see. We see the coil rotates, the coil cuts through the magnetic field, therefore inducing a voltage. And we notice the word cuts is bolded, magnetic field is bolded, and turns/rotate is bolded as well. So we would have to use those words. So when we're doing these questions, we need to be really specific with what language we're using. Okay, if you're double award, you can stop watching now. The next few spec points are for triple award only. So onto the triple award section of this topic, and onto the transformers section of the topic as well, where we need to describe the structure of a transformer and understand that a transformer changes the size of an alternating voltage by having different numbers of turns on the input and output sides. So a basic drawing of a transformer will look like so. Now this is what it would be known as a step-up transformer, as there are more turns around the secondary coil than the primary coil. So going into this transformer, we have a 10 volt AC supply shown here. Now that 10 volt AC supply will go through the primary coil. And in the process of going through the primary coil, a magnetic field will be produced, and that will be carried around the transformer by this magnetically soft iron core. Now, the fact that it's a magnetically soft iron core is really important because the iron core needs to be able to change direction of its magnetism really quickly. And that wouldn't be possible with materials such as steel, which is magnetically hard. So it needs to be iron, which is magnetically soft. So to recap, we have an AC current going through our primary coil. Therefore, when the current is going through the AC coil, we get a magnetic field created. Now that magnetic field is transferred through the iron core to the secondary coil. However, because it was an AC current, we've got a constantly changing magnetic field. And that constantly changing magnetic field is therefore transferred to the secondary coil. And because the magnetic field is changing, the field lines are being cut by that coil, or the coil is cutting those field lines. Therefore, we are inducing a voltage on the secondary coil. And because there are more turns around the secondary coil, there will therefore be a larger induced voltage around the secondary coil. And that induced voltage will also be an AC voltage. And in this case, there is double the number of turns, so there will be double the amount of voltage. And we can see that that relationship that we saw in the last example has an equation. So 6.19 is to know and use the relationship between the input primary and output secondary voltages and the turns ratio for a transformer. So our equation for that will be input primary voltage, so VP, that was our 10 volts in the previous one, over V secondary is equal to N primary, 4 in the previous example, over N secondary, which was 8 in the previous example, and therefore that's where I got that the V secondary was 20 volts from. Now we also have this equation that V primary times I primary equals V secondary times I secondary. And this equation comes from the fact that power must be the same through the primary coil as it is through the secondary coil, assuming there are no energy losses in the system. Now, we know that the secondary coil can't have more power than the primary coil because, well, we can't generate power for free. And if you can, well done, you deserve a Nobel Prize. So the equation P primary equals P secondary gives us the equation V primary I primary equals V secondary I secondary. And so this means if we have a step up transformer, the current in the output will be less than the current in the input. And if we have a step down transformer where we're reducing the voltage, the current in the output will be higher than the current in the input. So how does this come into practice? Well, it's really useful to know for the national grid. So the next spec point asks us to explain the use of step up and step down transformers in the large scale generation and transmission of electrical energy. Well, from our power station, we use a step-up transformer. And the main reason we use a step-up transformer to the high voltage transmission lines is to reduce the current. Having large amounts of current causes large amounts of energy losses as heat. So if we increase the voltage, we will therefore reduce the amount of energy losses in our transmission lines. However, we don't want kilovolts going to our consumers and homes and factories. That would be unsafe. So we use step-down transformers to bring the voltages back to safe levels for consumers. So our first question on this topic shows a step-down transformer, and it asks us to explain how a transformer works. And in our answer, we need to include reasoning for using 2 coils, the iron core, and an AC power supply. So we can start by saying there is a current through the primary coil, which therefore creates a magnetic field in the iron core. However, because we have an AC power supply, that is an alternating current, therefore we'll be creating an alternating magnetic field in the iron core. So that's our AC power supply part of this question done. But we've just mentioned the iron core, so we will go into that in a bit more detail now. The iron core boosts the magnetic field strength, and the iron core is a soft magnetic material, so it can change the magnetism easily, and it allows us for that magnetic field to change direction easily, which is really important because of that AC power supply creating a constantly changing magnetic field. Now, that constantly changing magnetic field, as we said, is passed through the iron core to the secondary coil. Now, therefore, the secondary coil interacts with this changing magnetic field, and therefore a voltage is induced across the secondary coil. And as we can see in this example, we have less turns on the secondary coil, and therefore the voltage induced on the secondary coil will be less than the voltage supplied on the primary coil. And if we check our answer against the mark scheme, we have it steps up or steps down the voltage. Current in the primary coil produces a magnetic field. The current is changing or alternating, causing a changing magnetic field in the core. The core strengthens the magnetic field. Idea that the iron is a soft magnetic material, i.e. it can gain easily and lose its magnetism easily. Field lines interact with the secondary coil, which induces a voltage in the secondary coil, and transformers won't work with steady DC. What we notice is lots of these mark points relate exactly to the 3 points we were given in the question to talk about. Marking points 4, 5 and 6 all talk directly about the iron core. Marking point 2 and 3 and 9 all talk directly about an AC power supply. It's really important when we see questions like this that we answer given exactly what the question is asking. We'll also be really careful to note a couple of the words that are in bold in our question here, which are the words induces and the field is in the core. So we're also asked to calculate the output voltage for the transformer, and this is where we use our formula that N primary over N secondary equals V primary over V secondary. And filling in our numbers from the question, we have that the N primary is 160, the N secondary is 45, the V primary is 12, and the V secondary is what we are trying to find out. With a quick bit of rearrangement, we have that V secondary equals 12 times 45 over 160, which gives our V secondary voltage of 3.4 volts. Notice how I've answered this 3-mark maths question by doing the equation, sum, answer, and then the unit at the end. And if we check our mark scheme, they show that they get 3.4 volts as well, with substitution, rearrangement, and evaluation marks. So our final question today is asking about the national grid, and it says there is a step-up transformer at the power station end of the transmission line and a step-down transformer at a distant town. Explain why step-up transformers and step-down transformers are used in this way. Well, first we can talk about the step-up transformer, which increases the voltage but decreases the current, and by decreasing that current, we are reducing the amount of energy losses due to heating in the wires. But when we get to the distant town, we need to use a step-down transformer, which will decrease the voltage and increase the current to make sure the voltage is at safe levels for people to use for their home appliances. And when we check our mark scheme, we see these same marking points of a step-down transformer increases the voltage, or a step-down transformer decreases the voltage. The step-up transformer reduces the current. Lower current means heating energy losses are less, but when we get to the town needs lower voltage for safety reasons so that their appliances operate correctly. Thank you for watching this video on electromagnetic induction. This has been the Abingdon Physics YouTube channel. Please leave a comment if you have any questions. Please also remember to like and subscribe to the channel. Thank you so much for watching. Bye.